So this is the 1-bit magnitude comparator added with the cascaded input, right? The center part of the box that is highlighted with the, this is the 1-bit magnitude comparator, right? This is the 1-bit magnitude comparator. With the same, I'm going to add a cascade input pins so that it can be extended up to n-bit comparator stage. The same method can be adapted to 2-bit comparator also that we discussed earlier, just driving the comparator output with the cascaded pin to achieve the final output. We see the configuration of the circuit. 3 AND gates are newly added, and all 3 AND gate 1 inputs it connected with the A equal to B of the 1-bit comparator. The AND gate equal to the AND gate that producing the equal to output, it is connected with a cascading pin of A equal to B, and it's producing the final output A equal to B. Likewise, the above and below AND gates are derived with the cascading pins of B greater and A greater respectively. But this AND gate is not producing the final output of A greater and B greater. It is connected to the OR gate. It is connected to the OR gate, and another pin of the OR gate is connected with the AND gate outputs of A greater and B greater pins of our 1-bit comparator. The reason is the cascading pins, these are the cascading pins. It means that we are considering from some LSB stages. Even in LSB, A greater will happens, but in the MSB, if it happens with B greater, then B greater output pin should be turned on. So let's see the operation. So initially we have A equal to B, 0 and 0. We'll select the poke tool. So A equal to 0, B equal to 0, but we are not attain the output A equal to B. So to attain the output A equal to B, we have to give A equal to B cascading input pin to 1. So this is the initial condition. This should be connected to VCC, and above and below pin should be connected to ground. Then only for 1 also it will become turn on. So if it is not happens, A equal to B condition will not work. The remaining condition will work, A greater and B greater, but A equal to B condition will not work, right? So to make that, we have to make this as 1. This is the initial setup. So this should be connected to the VCC, and above and below should be connected to the ground. So now A equal to B was turned on. Then in the new stage also we have A equals to B. So we got A equals to B. If A is greater, then A greater pin will be turned on. Then B is greater, then B greater pin will be turned on, right? Consider this are our A1 and B1, right? So this, it was connected from the previous stage. It means that LSB A1 and B1, now it is a MSB. So this was the output that is connected from the previous stage, that is A0 and B0. So we know that in the truth table, any one pin only will be turned on, either A equal to B or A greater or B greater. All the times, for all input combination, either any one output pin only will be turned on. So for example, now B greater was turned on in the previous stage, but here it is equal, but see the output, B greater was turned on, because B greater was turned on, LSB it was B greater, in MSB A equal to B. When considering both MSB and LSB, now B is greater. So for example, if in LSB B is greater, but in MSB A is greater, see the same condition, A greater was turned on. So for the same, if A is greater in the LSB, so it was turned on, and B is greater, but even though A is greater in LSB, in MSB B is greater, so B greater was turned on. So with the same, we can able to construct for 2-bit magnitude comparator also, and 4-bit, 8-bit. Thank you.